So I've been reading this application note from ST AN 1946. This application note is about sensing of the back EMF. It's called Sensorless BLDC Motor Control and Back EMF Sampling Methods with ST7MC. One of the things that caught my interest here is a schematic that I found at the end of this one. So this schematic is supposed to represent a kind of amplification stage for the back EMF in order to amplify the back EMF such that it is easier to measure back EMF when the speed is very low. And this is desirable. This is a very good feature. But the problem is that they don't really describe this schematic very well. The way that, like, if you think about it, what they're doing here is essentially they're adding a reference, they're adding an offset to the signal of the back EMF, and then they're amplifying it with a gain of, let's see, it'd be 1 minus like RF divided by R. No, sorry. It'll be 1 minus R divided by RF, I think the gain will be. Anyway, so they're amplifying this back EMF, and the diode here actually limits the input voltage to the op-amp to 0.7 volts, I think, depending on which diode this is. But they don't really give much information about the circuit. So I decided I would simulate a similar circuit, and I came up with this. So this is a really messy circuit, but such are things in LT-Spice because the user interface sucks. So everything that I create in LT-Spice is usually very ugly, and I don't really care about the way that this stuff looks. The only thing I care about is to be able to measure signals at different stages in the circuit. So I downloaded the model of this TLV247X class amplifiers, and I kind of modeled a similar circuit. So I found this circuit in the reference manual of let's see, at least part of this circuit was from the reference manual of the DRV chip. They set up a resistor divider that divides the voltage on each phase, and they clip the voltage to VCC. In this case, VCC would be 3.3 volts, and they filter it before they send it to the ADC. Now, this would be fine if it would be if precision is not really important, and what they're essentially doing here is that, let's say that, for example, this motor PWM runs at like 30 kilohertz. What they're doing with this capacitor is they filter out the PWM, so they get more like a kind of like a choppy waveform, which stabilizes at a certain voltage level, which would be the filtered back EMF. But this is rather simplistic. But I have drawn this schematic in LT-Spice, and previously I had the capacitor here as well, but I removed it for now. I can re-edit a bit later so you can see what happens when it's in place. But I adjusted the resistor values to represent the values that I have, and with such high resistor values, like in fact any kind of resistor values, the ADC precision suffers because the current is limited to the ADC, and the capacitor which is inside the ADC, which is used to sample and hold the signal, that capacitor cannot charge in time. So you need to have a longer measuring cycle set for the ADC in order to get a measurement. And I've seen that before when I was trying to measure these signals at certain precise time points during the PWM cycle. I would get wrong results. Like I would get very random results if the sampling time was too short. So what I want to do in this motor controller is kind of deal with this issue of not charging the ADC capacitor fast enough, and I do this by using the op-amps in this case. So if we just look at this circuit, which is the output of this resistor divider clipped to 3.3 volts, and I then pass it to through a 10K resistor to an amplifier that basically amplifies this signal. If we remove this resistor here and we simulate this circuit, then let's see. Then the output voltage would be kind of like a multiplication of the input, which looks like this. In this case, I'm running 48 volts waveform centered around 24 volts. I can offset it by 0 and simulate this again, and I would get a more good-looking waveform, because this let's see. Yeah. So because this resistor divider is designed to output 3.3 volts if the voltage is 48 volts. So everything is good here, but consider, for example, the case if the supply voltage is 24 volts. If we just use the resistor divider, we are instantly losing precision, because we are getting a signal that is now smaller than like the maximum range of the signal is halfway to what it should be. So kind of like sampling that signal is not really, it's going to be harder the slower the motor rotates and the smaller the back EMF is. So having an amplifier here is a very nice way to be able to handle different supply voltages and ensure that the circuit works exactly the same way. Now if I re-add this resistor, so let's see, let me just copy a resistor, because I think I changed the waveform there. So I'm going to copy, I'm going to duplicate this 10K resistor and just put it here. So now I've added an offset here, which means that the waveform that is amplified is actually now offset by the voltage of 1.60, like the reference is 1.65 volts, but then because of all the resistors here, because we have a resistor divider here and we have a sort of a resistor divider here as well, the resulting voltage is kind of not centered around 1.65 volts, but more like kind of like 1.1 volts. And setting these resistors properly ensures that the output signal can be between 0 and 3.3 volts and centered around the midpoint there. And the reason I also use an op-amp here is because I want to convert this voltage, which is coming out of these two resistors, into I want to have a 0 or close to 0 output impedance when feeding this reference voltage into the offset input of the amplifier. Because if I were to connect this directly to the resistor divider, I would get even more interference. So now I would have resistors that kind of interact all of them together, and I don't want that. I want to kind of isolate this this stage from the offset stage here. So the way I'm going to implement this now in my schematic is that I'm going to have a reference voltage which is going to be set by one of the stages in this op-amp chip, and the other three will be used to amplify the back EMF, and the amplification factor is going to be set by the two remaining I2C resistor dividers, or the I2C potentiometers, which I have left in the circuit for the overcurrent limit here. So I have two of them that are unused, so I'm going to use them as the gain for each one of the motors. So each motor will have the possibility to kind of like adjust the voltage gain of the backemf sensing circuit. And this output is very low impedance, so this output will charge the ADC capacitor very quickly. I'm going to put a small resistor here, like maybe 470 ohm or something, just so that the capacitance of the ADC is a little bit isolated from the output of the op-amp, and then I'll just feed this into the ADC, and I don't have to care about the extremely small current that flows in here. If you look at this resistor, for example, there is 160 microamps flowing through this 10K resistor. That's very, very little. And here it's like even like the positive. Okay, this is kind of like the opposite. So the positive is around 60 microamps, but it's still microamps. It's very, very small current. Now, if I put a resistor here, let's put like a 470 ohm resistor, and connect it to ground, then the current that will flow through this resistor is going to be much smaller, much bigger. Let's see here. So I'm going to place this here, and I'm going to simulate this, and then I can see the current here. So we get like 7 milliamps, or minus 7 milliamps. This is really this is really good way of conditioning the signal before passing it to the ADC. Why is it negative though? That I found a bit strange. So this flows there. Okay. It's interesting. So this actually flows backwards for some reason. Okay. So I'm going to remove this, and I'm going to start implementing the circuit in KiCad. I've started a little bit of design here, but it really wasn't correct. It wasn't the way it wasn't going to produce the results that I want. So what I want is I want one of these stages to be the reference that feeds into, let's see, so this would be the reference that goes, let's see, this would represent the offset of the input voltage. Come on. So I just divide the 3v3 by half, and then I feed each one of these amplifiers. So let's move that one there, and then we have a 5K and 10K. So that's correct, and and then 10K division here. So I'll move the voltage. So this would be the offset. Let's see. Yeah, and also this oh no, so this is not going to work. How stupid of me. I thought that I could use the same potentiometer to set gain on all of the amplifiers, but I can't do that because each one needs to be an individual circuit with the resistors connected such that the current can flow through this feedback loop. So it would actually be necessary to add another one of these potentiometers, which I'm not going to do because they're expensive. So I'm going to keep the resistors as passive components, and I'm just going to update the rest of the amplifiers here. And actually this is not going to ground, this is going to the reference voltage. So no, this is bullshit. Okay, let me just copy this manually. Nope. I'm gonna just copy this. No. I'm gonna copy this and connect signals here. Okay, so number 2 ready. And number 3. Maybe we should just place them like this, one after the other. and then this one will just go there. Okay. So this should provide enough drive to offset all of them. And I'm going to use the same structure for the, let's see, so let me just delete that. There we go. So then this op amp will provide half of 3D3, and then these ones will amplify the input signal, which comes from the circuits here. And in fact, I could keep the capacitors there, but they can be removed. Yes. So that's good. Now this bypass capacitor will be also placed somewhere here. This is easy enough. I'm just going to move this one here. Alright. And then we have the voltage sensing. This is for the motor voltage. I mean, this is not back EMF, this is VMOT, so this is the supply voltage for the motor. This is the general supply voltage. And I'm just going to copy this and I'm going to duplicate this block, and using the same concept kind of, and just copying it and renaming the labels. So this would be VSA2 and VSB2 and VSA2, VSB2. I've never seen this circuit being implemented this way, so this is going to be a very interesting test to do. And maybe if I realize that this is very useful, then I can implement variable gain on these amplifiers by making these two resistors part of an electronic potentiometer. So let's see, VSC2, VSC2. Okay. So that's it for the voltage sensing. And I'm going to just add a little bit of text here. And even though this is quite a new circuit, which I've never tested before, I think I'll leave the bypass resistors out of this, because if this circuit doesn't work, it doesn't really matter in revision A, because I'm not usually using sensorless drive. So this is kind of just to support sensorless control, but it doesn't have to be perfect the first time. So if this circuit doesn't work, the drive will still work, because the drive using encoder or Hall sensors will still function. Yeah, I can place that there. Okay. So one more thing here is this DC voltage, the DC voltage sensing. And it would be nice to have an op-amp stage there that just passes this filtered voltage through the op-amp and to the ADC. But in this particular case, I don't think it really matters, because there is already a capacitor here, which will be enough to charge the ADC capacitor, which is also, by the way, one reason that they put the capacitors there in this circuit, which is taken from the datasheet. So they put the capacitors there also because these capacitors help ADC capacitor to charge when it needs to sample the voltage on this junction here. So it has kind of a double function, both to filter the signal and to charge the ADC capacitor. Okay, so this is it for this video. I will continue to connect the remaining pins here on the schematic, and then it's time for a review, and when the schematic is done, it's time for layout. So stay tuned.